Even if we don't notice it, every second of your life is surrounded by millions of forces acting upon your body and every single object that surrounds you. In everyday language, we describe a force as a push or a pull. But in mechanics, we know that a force is an interaction between two bodies, or between a body and its environment. So force is something that one body exerts on another. And it is also a vector quantity, meaning that it has a magnitude and a direction. Whether it is gravity keeping your body on a couch, or normal force, which any surface exerts on an object. Forces are all around us, but today I'm going to talk about a force that I see every day of my life. Let's talk about tension. The pulling force exerted by a stretched rope, cable, chain, or cord on an object is called the tension force. Because it is a force, we have to measure it in newtons. This force can be equal to the weight of the body, which is mass times gravity. Let's look at a very simple example of tension, which my cat Machi exerts on her toy every time she pulls on it. In order to figure out the tension she's exerting on the string, we need to figure out what her mass is, because we need to multiply times the gravity of Earth in order to get the tension. And after weighing my cat, I figured out that her mass is equal to 4.1 kilograms. If we assume that Machi is using all her mass to pull on the object, the tension will be equal to her mass times gravity. So we multiply her mass of 4.1 kilograms times 9.8 meters per second, and we obtain a tension of 40.18 newtons. Now it's important to note that newtons are equal to kilograms times mass divided by seconds squared. Now let's look at a more complex example, where tension on both of the strings that we have is not going to be equal. Now our weight is distributed between two massless strings. We will assume they're attached to a ceiling, which will be our green line. We need to figure out the tension between them, but for now, let's figure out the angles, which are 51 degrees and 56 degrees. If we don't have equal angles, we won't have equal tensions. For calculations, we'll have to break it up into x and y components because of our angle. For our x component, we are going to subtract the tension of our first spring times its cosine minus the tension of the second one times the cosine of the angle, which will be equal to 0 since we have a system at equilibrium. Now we will clear for T1 and obtain the following equation. Let's move on to our y component. For our y component, we're going to have an addition from the tension of the first string times the sine of its angle plus the tension of the second one times the sine of its angle minus the weight. Weight only has a vertical component here. What we want to do now is grab the value from T1 that we obtained in our first equation and plug it in into our y component equation. Now that we plug it in, we're going to do addition, and we're going to notice that we only have T2 values here. That means that algebraically, we're going to be able to clear for T2, which now will be equal to 26.44 newtons. We are going to grab that value that we obtained for T2, and we're going to plug it in into our equation that we found at first for T1. After that, we are going to find out that T1 is equal to 23.49 newtons. Now we know how much tension force Machi is exerting on our first string and our second string. Now these were just a couple of ways in which I see tension in my everyday life. But every time you see a car being towed, or you play tug of war, or a crane is used in construction, tension force can be found. And this is just one type of force. Spring force, electromagnetic force, normal force, they all take a role in the way our world works. So thank you so much for watching my video, and good luck on finals.